A very good morning to one and all. Today, we are going to discuss about the latch up in Cmos and also the Bicmos. And also, we can just brief discuss introduction about the second unit, that is different MOS and Bicmos circuit design process. Okay, that is unit number 2. Okay, now let's go to concentrate on latch up in Cmos circuits. Okay, so what is a latch up and how to prevent the latch up in the Cmos circuit? We'll discuss in this class. Okay, so now just go for before going to latch up. Okay, before going to latch up concept, just you can see the structure of N well as well as the P well. Okay, so just I'm briefly explain about N well and P well structures. Okay, so now I'm going to share the screen now here. Okay, now just observe. This is the structure of PL, CMOS PL. So as you know that CMOS circuit, the name itself indicates the complementary left side semiconductor field effect transistors. Okay, CMOS technology. So in the CMOS technology, we are having complementary transistors. We are using complementary transistors. So therefore, in order to get the complementary transistors, so actually, what we require the N-channel enhancement mode transistor. Again, we require the P-channel enhancement mode transistors. So we require the two type of transistors, and we require the two substrates like this. Okay, again, two substrate on the N-channel. In order to construct the N-channel FET, we required P substrate. Similarly, in order to construct a P-channel field effect transistors, we require N substrate material. Okay, instead of using two substrate materials here, so we are going to use same substrate material in order to construct both the N-channel as well as the N-channel as well as the P-channel field effect transistor MOSFETs. Okay, so this is the concept now here. That means we can use here the well structures. Okay, in order to construct the two transistors, there is the N-channel MOSFET as well as the P-channel MOSFET in a single silicon. So we require a well structures. Okay, that is the main important thing in this case. So just observe here in the P-well structure, the P-well. Okay, in the P-well structure, the main substrate is the N-type semiconductor. This is the N-type semiconductor. In the N-type semiconductor, we are going to construct N-channel FET. Okay, this is the structure. Sorry, this is the structure of N-channel substrate. We are going to construct with a P-type substrate. Okay, so the P-well we require. Okay, basically, yes, remember here. This is the N-channel. Okay, so this is the N-type substrate. Basically, this is the N-type substrate. So in the N-type substrate, we are going to construct a P-type transistors, right? In the N-type substrate, we are going to construct a P-type transistor, that is pull-up transistor, you can say. Similarly, in the same N-type substrate, in order to construct the N-channel FET is difficult. Okay, listen. Because only on the substrate, in this substrate, we construct only P-type transistors. But in order to get the N-channel FETs, the same structure, we are going to make a well form, very well structures. Okay, so that means we are going to deposit P-type substrate on the N-type circuit. Okay, P-type semiconductor. Okay, this is the N-type semiconductor. So on this N-type semiconductor, we are going to construct a P-well by using P-type semiconductor. We are going to deposit a P-type semiconductor. P-type material here. Okay. So on the P-type And this p-type semiconductor behaves like a well. Okay, this is one well. Okay, this is the form of well here. Okay, so and this well behaves like a substrate terminal. Okay, this behaves like a substrate for n-channel FET. Okay, just remember this is the n-channel FET. Okay, and in the n substrate we are going to construct a p-channel FETs. Okay, now just see here, this is the hashings of the p-channel and this is the hashings of the n-channel. Okay, the line should be small here. The two hashing, the separation with the two hashings is very, very small, and the separation with the two hashings will be very high. Okay, so that means this is the p-type material, this is the p-type material, and this is the n-type material, and this is the n-type material, right? So this is the p-type material. Just remember here, this is the p-type material. This is used like a drain, and this is used like a source terminal, right? Similarly, this is the well structure. In the well structure, okay, what type of well here? This is, so this is the P well. Okay, this is the P well. That means this is the p-type semiconductor. On the p-type semiconductor, we are going to fabricate n-type layer. Okay, we are going to deposit n-type material, heavily doped n-type materials like this here, and so this is also n-type material. At the same time, we are going to connect the source to the ground, that means VSS terminal, and the drain to the VDD terminal. And remember, because of this, we are having a structure like this, a well structure, we require another two materials here. Okay, this is for, okay, this is the substrate connection. Okay, this is the substrate connection, and this is the well connection. Remember that point. So in the substrate connection, okay, we are having, we require the n-type substrate. Okay, we require the n-type material, every doped material, basically is the n-type material. So in order to distinguish the substrate and the diffusion, okay, we are having this is n and this is n material. It's an n-type substrate. Your hashing should be like this, and n diffusions, you are having the hashing should be like this. Similarly, for the P well, okay, we are having this is the hashings, and this is the hashing for the P material. Okay, that means this is required to connect the VSS terminal. This is, that means you can supply to the substrate terminal also. Okay, because already we discussed, when the substrate terminal not in use, always connect the substrate terminal with the source terminal base connect. Okay, so that is the main thing you have to remember. But in this case, whatever the concept in this case, the p-type substrate. Okay, so this is the p-type substrate. Okay, this is the p-type semiconductor. Remember the point in this case. This is the, what is this p-type semiconductor, the source terminal. Okay, this is the source terminal, and this is the drain terminal. Okay, in the p-type transistor. But come to the n-type transistor, this is the drain and this is the source terminal. Okay, so this is source and this is source. Okay, so therefore this is the substrate connection. This is the well connection connected to the source terminal. This is the substrate connection. Okay, so don't forget in this case. This is very, very important in order to draw the layout diagrams. Okay, these are the most important concept in this case. Remember that point. To activate the substrate structure, we require the power supply connection like this. Substrate is connected to the, when this is not in use, always connected to the source terminal, and this also connected to the source terminal. Remember like this. So this is the structure of the CMOS PWEL circuit. So in this PWEL structure, already we discussed now, we can construct same two transistors, the same silicon, with the same single silicon. We are going to deposit them. We can construct the n-type n-channel FETs in the PWEL and p-channel FET in the substrate. Similarly, in n-well, okay, you have another method, that is n-well structures. You can construct the n-well structure also, but exactly opposite. So in the n-well, whenever you can see well structure, n-well means substrate must be p-type. So this is the p-type substrate. Okay, and like this you can construct exactly opposite. Okay, this becomes n-well and this becomes a p-well. Okay, in the p-well we are going to construct n-channel FET, and like this we can construct all the method like exactly. So whatever the layers is there here, we are going to take the opposite layers. Okay, that is about the Cmos N-well process. Okay, now let us consider what happened. What is the meaning of now our discussion in this case is latch up. Okay, because we are having number of junctions in this case. Okay, let's go for the previous structure only. We are having number of junctions. See, this is one junction and this is another junction. This is another junction. Like this, we have number of junctions. So because of this junction, what happened is, so as we know that every semiconductor, whenever the junction is formed, okay, so what happens? A diode will be exists. Similarly, because the doping concentration of the N-well and P-well are in terms of substrate and the P substrate, so what happens is the resistance of the transistor also changes depending upon the doping concentration. So that means there is a chance of existence of resistance that is called these component. Okay, whatever the diodes and capacitance and also the resistance, or the nothing but parasitic component. Okay, there is a parasitic component. So, but in case of previous structure, not only the resistors and capacitance will exist, but also you can get transistor parasitic components also, parasitic transistor components also. Okay, so that is the main thing in this case. So whenever because of this parasitic component, because of this parasitic component, there exists a low resistance path. Okay, there exists a low resistance path between VDD line and VSS line. Okay, because of this parasitic component, there exists a low resistance path between VDD line and VSS line. This low resistance path will be very, very dangerous. It is undesirable. So therefore, this undesirable condition is known as latch up in the CMOS structure. Okay, this undesirable condition is known as latch up in the CMOS structure. So latch up means the existence of, because of the parasitic components, there exists a low resistance path between VDD line and VSS line. So that is the type of condition is known as latch up, right? Now let's see the structure of latch up in this case. Okay, let's go for the previous structure. This is the previous structure, latch up in the CMOS structure. Now already discussed now. So there exists a latch up mechanism. So again, just observe here. Okay. So now you see this is the substrate terminal. Okay. So the doping concentration, depending upon the doping concentration, there exists a parasitic resistance component here. That because the doping concentration, the conductivity is increases as well as the resistivity decreases. Now we are having compared to this material. So this material is having some moderate doping concentration. So because of the moderate doping concentration, the resistance of the substrate is high. Okay, let us consider this is the substrate resistance of the material. Okay, silicon. This is the silicon material, and this is the substrate. This is the parasitic component. Okay, basically we are not going to use the resistor, but it exists during the operation. Okay, this is the because of the doping concentration there exists a resistance. Similarly, this is the P-type semiconductor. Okay, heavily doped P-type material, and this is the moderately doped N-type material. Okay, this is the doping material, and also we are having this observed in this case the P-well structure. Okay, this is the P-well structure. So depending upon this is the P material. Okay, that means this is the P material, this is the N material, and this is the P material. That means inside the silicon, single silicon, we are having a PNP transistor. Okay, we are having a PNP transistor, N material, the substrate is the N-type material, and well is the P-type well. Okay, because of the P-well structure. So because of this well structure, we are having a transistor here. Okay, just remember. So this transistor is the one parasitic component. Okay, similarly, in the well, it is also having some doping concentration. Depending upon the doping concentration, there exists some amount of resistance in the well structure. Okay, this is the P well. So there exists a resistor, you can consider as RP. It is also a parasitic component, and at the same time, similar to the T1, there is just observe. This is the N material. Okay, this is N material, and this is the P material, right? And this is the another N material. Okay, this is another N material. So therefore, substrate is another N material, right? So because of this substrate material, N material, so what happens? There is a chance of existence of NPN transistor. Remember, this is the NPN transistor. Okay, because of the different junctions inside here, so there exists these type of parasitic component. So whenever this type of parasitic components exist, there is a chance of existence of a low resistance path depending upon the voltage drop across RS and RP. Okay, because during the operation, so what happens? Some amount of current will flows in the resistance in the substrate material or as well as the previous structure. So what happens? Some current the voltage will be developed, and that voltage is able to drive the transistor T1 and T2s. So therefore, what happened now? These transistors will be conducts. Okay, so when the two transistors will be conducts, so what happens? There exists a low resistance path between the VDD and VSS line. So this is the type of path is known as the latch-up condition in the CMOS structure, and this latch-up is undesirable. Okay, so there is the main important thing. That means, so latch-up is, remember that point, latch-up is a undesirable. So our aim in this case is to avoid this latch-up. Okay, our aim is to avoid this latch-up. How to avoid this latch-up in this case? By during the fabrication process, steps only. Okay, during designing process or fabrication process, you can avoid this latch-up condition. That depends upon the depth of the well. Okay, the well depth cannot be very high. Okay, it must be sufficient. Otherwise, there is a chance of existence of latch-up. Okay, that is another very important thing. Similarly, you can use the guard rings in the structure to remove the latch-up in the circuit. Okay, that is about the latch. So what is the meaning of latch-up? There exists, just remember, this is the transistor, there exists resistance, substrate resistance, and this is the well resistance, and this is the well transistor. Okay, this depends upon the transistor here. So it behaves like a silicon control rectifier. Okay, this is behaves like a silicon controller. But the equivalent circuit, the latch-up will be like this. So there exists a latch-up in the circuit. Okay, remember. So therefore, this latch-up is very undesirable. Okay, this latch-up is undesirable. So depending upon the subserve norms, this I'll explain about this one. To the subserve, whenever the current flow through this resistance RS, okay, and when the voltage across this resistance RS is sufficient, okay, so this will turn on this base emitter junction. This is the emitter and this is the base of the transistor T1. So what happened now? The drop across this one is actually it is around 0.6 volts approximately. Whenever the current flow through the resistor, the substrate material, there exists a voltage drop, and that voltage drop turns on the transistor T1. Similarly, so what happened now? This is the emitter, this is the base terminal. Whenever there is a current flow in the well structure, what happens? There is some amount of voltage drop across the resistance RP. That voltage is across the base and emitter of the transistor T2. So assume that when the two transistors will be turned on, there exists a low resistance path between the emitter and collector. That means just observe the very low resistance here. Because when the transistor will be entered into saturation, so this transistor also enter into the saturation. So both the transistors will be turned on, so there exists a low resistance path. So because of this low resistance path, what happens? This point will be connected to the VDD like this. Okay, it will be connected to the VDD because of the low resistance path. There exists a low resistance path. Just remember. So when these 2 points turns on, so there exists a low resistance path between the collector and emitter of the transistor. So therefore, what happened now? The two transistors will be turned on. Okay, the transistor will be turns on. So what happened now in this case? When the two transistors turns on, there exists a low resistance path between VDD line and VSS line. Right. So remember that point. So just see. So from this point, the transistor point will be exist, the current flow like this, and go to the VSS line. So similarly, there is a chance of voltage current will be exist in this case. So there exists a low resistance path because of this parasitic component. So what happened? The current will flow from VDD line to VSS line. This current is undesirable. So because of this current, what happened? The power dissipation will be very high. At the same time, the transistor will be destroyed. Okay. So because of this, what happened? Okay, because of this latch up, there is a chance of existence of a breakdown condition of the transistors, and also in order to avoid this one, so this remember that. To avoid this one, what to do now? You can fabricate perfectly in this case. Otherwise, so what happens? The latch up will be exist. So that means you can get there must be sufficient depth of the well we required. Okay, wells must be remembered. So that is the main important thing. So that means just observe here. So that is the main important thing in this case. Right. Biotech silicon control test. Okay. To avoid this latch up, so that is the main important thing. You can use what happened? You can increase the doping, decrease the doping concentration in the substrate material. Okay. If you decrease the doping concentration in substrate material, what happens? The current flow through the resistance value be decreases. Okay, resistance value be increases. Okay, decreases. So that means to avoid this latch up condition, to avoid this latch up condition, you can increase the doping concentration of the substrate material, or you can increase the doping concentration of the free material. If you increase the doping concentration of the substrate material, what happens? The resistance of the RS value will be reduced. If the resistance value be reduced, the voltage drop is reduced. When the voltage drop is reduced, what happens? The transistor T1 will be turned off. Okay, so this parasitic transistor will be turned off. Similarly, you can increase the doping concentration of T well. So what happens? The drop to the resistance will be reduced. So similarly, same concept. Voltage drop between the base and will be reduced. The transistor T2 will be off condition. So therefore, so there is some problem. So okay, the doping concentration substrate cannot be very high. Okay, so that is also very important. And the doping concentration value also not be very high. Okay, so that means the depth and doping plays a very important role during designing process. Application, you have to take care of all these things in this case. Okay, so that means remember that means you can increase the substrate. That is the first thing. You can increase the substrate doping so that resistance RS will be reduced. Okay, the drop of doping. Similarly, so that is the main important. If you reduce the resistance RP, what happens? Okay, how to reduce the resistance RP there during the construction only. So because of that, what happened? Low resistance path will be reduced. Reduce the resistance RP. Right. So that means we are having two mechanisms, two conditions here. First condition is to reduce the resistance RS so that the transistor T1 is off condition. Any one transistor will be off condition, then the latch up can be avoided. Or you can reduce the resistance RP, you can reduce the the transistor, so that there is no chance of existence of low resistance path in the VDD and VSS line. Okay, so there is the most cases you can use the guard rings. Underway, the mostly used methods in this case cannot reduce the resistance. Okay, we cannot reduce the resistance, cannot increase the doping concentration of the substrate material, or cannot increase the doping concentration of the well material. So that therefore, you can use the guard rings in order to eliminate the this latch up condition. That is the main important thing. Okay, there is about the latch up. There exists silicon control rectifier. Okay, this is the same form of resistance, transistor T1, T2, and RP. Used like a silicon control rectifier. So remember that one, right? That is about the latch up in the signal. Similarly, if you go for the latch up in the Bicmos also. Okay, this is the Bicmos latch up condition. Is not a. This is the another thing is this is the latch up in the NVL process, the Cmos structure. Okay, this is the latch up, the same mechanism there also. So here in the well structure, we are having PNP transistor. Here we are having NPN transistor. We are getting a parasitic component, that is the NPN transistor. The resistance of the substrate is the resistance of the well. So therefore, there exists a low resistance path depending upon the operation. Right? That is the main thing. You can reduce the operation. You can reduce the same method. Previously, what the topic we discussed there. You can increase the doping concentration of the well, or you can increase the doping concentration of the substrate. So this substrate, you cannot increase the doping concentration of the substrate material because the threshold level of the transistor will be affected. So therefore, we cannot go further with the doping concentration. Similarly, the doping concentration here also we are not going to increase because that will change the threshold level of the transistor. So therefore, we cannot increase the threshold level. Instead of that, we are going to use the guardrails in the Cmos technology. Similarly, that is about the latch up mechanism. Right? Now, similarly, we are having the Bicmos latch up also. Okay, so these are the Bicmos latch up structures. So they can be how to eliminate the latch method. Okay, you are having latch up problem. Okay, so that means in the Bicmos, you can how to reduce the latch up mechanism. So the reduction in substrate resistance RS. Okay, same method. This is also same thing in the N-well. Similar reduction in the N-well resistance. Similar reduction in the RS and RW. So okay, mean these are the reduction in the RS and RW means large amount of current will flow. In the large amount of current, what happened? So there is some holding current will exist. All these things you have to remember. Because, okay. Similarly, the PNP transistor, there is the same concept. Okay, there is the beta factor. That means that you reduce the beta factors. So beta factor also very, very important. Current amplification factors. Okay, B1, B2. Okay, these are also very, very important in this case. Okay, so these are the latch up in the circuit. Another very important thing in this case is because the reduction in the value of resistance RS, what happens? The current is increases. When the current is increased, automatically beta factor will be changes. So therefore, to reduce the latch up mechanism in the CMOS process, that these we are having two transistors there. Okay, one PNP transistor and the NPN transistor. The beta of the transistor must be such that okay, the product of the beta 1 of the transistor and the product of the beta 2 of the second transistor must be greater than 1. Then only the latch up can be avoided. Okay, so latch up may occur. Okay, that is the main important thing. So when the beta 1 and beta 2 is greater than 1, the latch up automatically latch up will exist. So always the beta 1 and beta 1, beta 2 is always less than 1 to reduce the latch up mechanism. Right? These are the main thing you have to remember in the latch up condition in the structure. Okay. Next, we will go for the next topic is that we will go to the unit number 2. Okay, there is MOS and BiCMOS circuit design process. Okay, this is a very, very important structure. From now, we are going to enter into actual VLSI chapter subject. Okay, so the MOS and BiCMOS circuits. Okay, basically, in the MOS and BiCMOS circuit, basically we are having this is nothing but here we are going to take the design process. Okay, MOS and BiCMOS circuit design process. Unit number 2. So in this case, we are having different type of layers. So already we discussed. Okay, so we are having number of layers in the different field effect transistors. Okay, substrate material, source material, and drain material. So these are diffusing process like this. Okay, N channel and P channel and polysilicon like this we are having. So therefore, we are having different MOS layers. Okay, you can aim on this case here. In this case is you have to consider the 4 basic layers basically. Okay, they are first one is the N diffusion and P diffusion and the polysilicon and the metal. Okay, these are the most important layers in the MOS structure. This is the N diffusion, very, very important. Okay, and P diffusion also very important. Okay, so in case of N channel FET, okay, N channel FET, N diffusions are very, very important because the drain and source are N channel material. So the P channel material, P channel transistors. So diffusions are nothing but N. Okay, P material and the polysilicon it is used to identify the gate material. Already we are seeing the structure. Okay, polysilicon that is the we can use the polysilicon between the gate terminal and the silicon dioxide layer. So there is a polysilicon. This is only you can use only at that area only. So that's why the polysilicon is the most important metal. Similarly, metallization. You can use it by using a metal. So that means this is the metallization. That means the 4 metal layers we require now. So 4 layers are required: N diffusion, P diffusion, polysilicon, and metal. Okay. N diffusion, P diffusion, no problem. Polysilicon is also common. But the metal, we are having different type of metals. Depending upon the type of technology we are going to use it. We are using metal 1, metal 2, and metal 3 also. Okay, metal 1, metal 2, metal 3 also. But in case of Cmos technology, you can use only metal 1. But in case of Cmos technology, you can use metal 1 and metal 2. And the polysilicon also, we are going to use different type of polysilicon 1 and polysilicon 2. In the BiCMOS technology, we are going to use the polysilicon 2 also. Okay. So like this, we are having different type of layers. There is 4 type of layers we are going to use in the MOS structures. Okay. Depending upon the MOS reasons, we are having different layers. Okay. Next one is the stick diagram. What is the stick diagram basically? Okay. So basically, stick diagram is used to convey the layer information through the use of color code. By use of color code. That is the main definition. Stick diagram means we convey the layer information by the use of color codes. That is called stick diagram. Okay, that is known as stick diagram. Okay. Now let's see what is the different type of color. So already we discussed there are 4 layers. One is N diffusion layer. So this N diffusion layer can be represented by using a color code by use of green color. Okay, by using a green color, you can convey the information. By seeing this green color, we can say that this is the N diffusion layer. Similarly, here having P diffusion also, no problem. Depending upon the same time, green color or sometimes the hazing will be different. Okay, there is also changes depending upon the NMOS technology as well as the PMOS technology or the same CMOS technology. Okay, and the polysilicon it is used. The color code for polysilicon is red color, and similarly metal. Okay, the color code for the metal is blue color. Okay, these are the main colors in the NMOS fabrication, NMOS stick diagram. Okay, that means we are going to represent the different layers by the use of these color codes is known as stick diagram. Okay, to convey the layer information by the use of through the use of the color codes that is known as stick diagram. Okay, so what is that now? How to draw the stick diagram? Okay, that is also very important. So we are having different type of encoding process. Okay, so we are having encoding different type of encoding process. In NMOS technology as well as the PMOS technology, also we are having these encoding process. Okay, so to draw this stick diagram, we require these are the layers. Not only these layers, we are having different type of points as you have to remember. We are having encoding procedures for NMOS technology. Okay, what are the encoding procedures for the NMOS technology? Let's just observe here. Okay, this is the encoding process. Okay, now just observe here. Here having yellow color, green color. Okay, different type of encoding process here. The first one is that I go for the green color. So okay, basically we can use the green color for N diffusion. The green color is used for N diffusion. Remember, this is the N diffusion is used for green color in MOS technology. Green color is used to identify the N diffusion layers and also N plus active FINAX. We will discuss what is FINAX layer. Okay, we'll discuss what is FINAX layer basically. So N diffusion plus D diffusion plus transistor channels are nothing but FINAX layers. Okay, remember FINAX layer nothing but N diffusion as well as the P diffusion as well as the transistor channels combinedly. We consider the FINAX layer. Okay, or N diffusion transistor channels, P diffusion or transistor channels is nothing but FINAX layer. Okay. Similarly, red color. Okay, we are having a red color. So basically, red color is used for identification of the polysilicon. Okay, Red color is used to identify the polysilicon. Okay, right? So remember, red color is used to identify the polysilicon. Okay. Similarly, we are having different layers. Okay. So that is blue color. So blue color is used to identify the metal one layer. Okay. Blue color is used to identify the metal one layer. Okay. So that is also very important. Similarly, here we are having another term that is a SIF layer. Basically, SIF layer is nothing but Caltech intermediate form. You can represent the CAF is the Caltech intermediate form. So this is basically used to describe the integrated circuit. Okay, different layers in the integrated in the two-dimensional structure. Okay, so that is also very important in this case. But basically, we can avoid this SIF layer in order to analyze the structures here. So these are the green is used to identify the diffusion finance layers, and red is used to identify the polysilicon, and blue is used to identify the metal one layers. Okay, remember this is the metal one layer. And similarly, we are having black color. Okay, so black color is used to identify the contact cuts. Okay, the contact cuts. So this is the contact cut. Okay, we are having the circle surrounded by the black color. That is called contact. In the same method, we are having the contact cut. Similarly, here gray color. Basically, it is Cmos technology. This gray color is particularly in case of stick diagram, there is no gray color. But basically, you can use in the layout diagrams, you can use this gray color for overglass. Okay, we are having overglass. Okay, gray color particularly this overglass, or particularly when you use in the layout diagrams, not in the stick diagram. There is no overglass method. It is a stick diagram, but you can use it in the layout diagrams. Okay. Similarly, so these are the different layers. You can encode by using black and white, or you can use the color. If you use a black and white, that means by using a pen and pencil, you can draw the structure like this. You can draw the structure for different layers. Okay, so for diffusion, you can use the green color, and for green color also. Otherwise, you can draw the lines only by using the colors. Okay, in case of stick encoding. But monochrome condition, you can draw this type of layers. Okay, I will show. Right. So there is a main thing in November. We'll discuss about that one. So this is the main important thing in this case. So basically, the MOS structure, we're having 4 basic layers. One is diffusion, pre-diffusion, polysilicon, and metal. So not only these layers, again some additional layers of contact. There is the contact cuts, and also some different layers will be there. There is the black color and the blue color. So all these layers were having. Okay, and sometimes we are having different some other colors also. There is the black color and brown color. Okay, but in case of Cmos structure, we use a brown color. Similarly, you can use the yellow color. In case of Cmos technology, the yellow color is used to identify the depletion mode transistors. Remember, it is also very important. Okay, yellow color is used to identify depletion mode transistor by placing implant. Okay, that is called implant. The structure of the implant will be dotted lines surrounded by a rectangular form or a square form. By a like this. Okay, yellow color. Okay, not only the stick diagram, the layout diagram also. Okay, similarly, brown color, that is very important thing in this case. So we're having in Cmos technology, we're having a different type of contacts. The ordinary contacts, we're having some special contacts, which are buried contact and butting contact. Okay, so we have different in order to join 2 different layers. You can remember in the layout diagram, a stick diagram, whenever you make a contact, so that means because we are going to convey the layer informations here, so therefore whenever the two different layers we join together, we must require a contact. Okay, we must require a contact. If you have this, in order to join the two same layers, no need of any contact. Just whenever the two layers will join together, okay, two same layers will join together, no need of any contact. Automatically, you can directly use the contact there. But whenever you can use the two different layers, for example, you want to join metal and diffusion, you require a contact. Or if, in order to make a diffusion or polysilicon, you make a contact. Okay, so but no need of any contact with the diffusion will exist. You can't, I mean, the polysilicon to polysilicon and blue, green color to green color. That is the metal to metal, metal one to metal one. No need of any contact. Okay, whenever the two different layers join together, we must require a contact. Okay, that is also you're having different type of contact there. One is butting contact and also buried contact. Okay, so but remember, the buried contact cannot be used in Cmos structure, and the buried contact is used. The color code for this buried contact in the Cmos technology, because the buried contact is used only in the Cmos technology. So the buried color code for this buried contact is brown color. Okay, so whenever we require a brown buried contact, just cross a particular area by a circle and then fill it by a brown color. That is nothing but to identify that buried contact. Okay, so that is about the different type of color coding or encoding. But now, so these are the different type of encoding process. Okay, green color can be represented with stick encoding like this, but layout you can represent like this one. Okay, having start from the top right corner and closes at the left down corner. Okay, so these are the hashings of the end diffusion layer. Okay, and this is the red color. This is the same structure. Structure is same, but the color will be different. Okay, layers. That's all. So, for example, this is the horizontal line. You can draw. For example, it may be vertical line also. And whenever we require another layer, connect the other layer, the same layer. No need of any contact here. You directly connect the layer point. Similarly, same layer. You can connect like this. No problem. Okay, there is a blue color. And this is nothing but the layer as is layout information. Okay, that is mask layout. You can call it as a mask layout. Okay, diffusion basically. What is the diffusion basically? Cmos. Cmos is ordered with Cmos basically. Then diffusion plus transistor channels. Now, what is the transistor channel here? So in this case, whenever just remember, the transistors are nothing but you're having N, for example, go for the N channel FET, the channel is N type material. Okay, N channel FET, the channel is N type material. Okay, so whenever and how to get form a transistor here, whenever you're having a gate terminal. Okay, so therefore the gate terminal is nothing, you can identify the gate terminal by using polysilicon. So therefore, whenever a polysilicon crosses the diffusion layer, transistor is formed. Just remember, whenever a polysilicon, this is the polysilicon, color for the polysilicon is red. Whenever the polysilicon crosses the diffusion layer, okay, whenever the polysilicon crosses the diffusion layer, must cross. Okay, remember, okay, crossing must exist. If there is no crossing, you can draw like this only. What happens? There is no transistor form. So in order to make it, in order to get the transistor form, okay, that means in order to form a transistor in the stick diagram, so we must cross the diffusion layer by a polysilicon. Okay, you must cross. Okay, that is the main structure. So this is the structure of the transistor now here. Just observe here. This is the end diffusion, and there is a process like this. So this is the transistor. What type of transistor? The N channel. Green is used to identify the N channel, N diffusion. So therefore, so this is the formation of the transistor. Whenever the polysilicon, the red color crosses the green color, a transistor will form, right? And this is the layout diagram. Just remember, this is the layer. Okay, this is the blue, the green color. This is the N diffusion, and this is the polysilicon. So when polysilicon crosses the, just remember, polysilicon, it must cross here. Okay, then only the transistor is formed. So there must be crossing. Otherwise, the transistor will not form. So there is the main important layout. And these are the symbolic layout layers. Okay, this is symbolic layer, and this is the previous item, the mask layers. Okay, mask layout series. This is called the layout. Okay, so this is about the Cmos encoding. Okay, remaining we'll see in the next class, right? Okay, next now I'm going to stop the screen now. We'll see in the next class.